Hello, everyone. Right, so I hope you've seen the assignment on momentum. Oh, probably have. Hello, yes, good to see you. Talking about momentum, I have done at least 3 webinars on momentum. So if you are, if you're still confused after today, please watch my other webinars. I'm doing a completely new webinar, so I'm not repeating myself, hopefully, except the first problem, perhaps, because it's so important. And yeah, so I'm going to start quite easy today, and then move on to medium difficulty problems. And we're going to go slightly off topic. We're starting going to dip into topic number 6 as towards the end of the session. So this is what to expect: momentum. I've done several webinars on momentum, so please watch those if you are unsure. Okay, so let's get on with things. Perfect. So I'll share my screen. And yeah, okay, that's what I want to do. The chat, of course. I want to see the chat. So you should be able to see my screen. So momentum is a vector quantity. Momentum is mass times the velocity, and because mass is a scalar quantity and mass and velocity is a vector quantity, then we have a vector quantity. If mass was a vector quantity, then depending on what kind of multiplication we would have either a vector or a scalar. Yes, for example, work is force multiplied dot product by displacement. Right? So vector, vector, scalar. Scalar, vector, vector. But moment of a force, you've heard about moment of a force, is force multiplied by the distance, or well, distance to the pivot, or you can say displacement as well, sort of. And it is a vector, because these are two different types of multiplication. I'm not going to go deep into this, just a peculiarity. There's something that came into my mind just now. You're multiplying the same property. Well, not, we never call it, we call it d, distance, displacement. Sorry, distance from the pivot. So in a moment is a vector quantity, whereas work is a scalar quantity. And yeah, but when you multiply a scalar by a vector, you always get a vector. There's nothing you can do about it, basically. Anyways, since you don't take account of the direction, of course you do. It's perpendicular distance. Yeah, when you are doing it's perpendicular distance, so it's a projection of a vector onto the perpendicular. So if you have a pivot, and there's a force, and this is the distance, I don't know, to A. You take the perpendicular, so you take the component of the distance which is perpendicular to the vector. No, it's more complicated than that. Moments is a tricky topic if you do it in terms of vectors. That's why they don't teach you vectors in moments. So if you have a pivot and a, I don't know, seesaw, and there's a force here, and this is the displacement vector, R, let's call it R1, and this is F1. And if you take vector R2, which is like this, R2, you can clearly see that they're in opposite direction. And the force F2, for example. You can clearly see the vector R1 is opposite to vector R2. Therefore, you would need that when you multiply, the moment 1 is F1 vector times R1 vector, and moment 2 is F2 times R2. And the directions would be included in here. Now, what you normally do is you say clockwise versus anti-clockwise, and it just simply means clockwise are the ones that will have a positive sign, and the negative and the negative one. But hope is orthogonal. What is orthogonal if it's a vector? And oh, you mean the perpendicular? So if this is a vector, this is the point of application, right? But it doesn't have to be here. So for example, if you have a more complicated case, so you have a pivot, which is here, pivot, and you have a force applied here, F1, and you have a vector to the point of application here, R1. And then you have a vector R2, and the force is like this, F2. The moment is just the multiplication of the two vectors. So you don't have to worry about if it's clockwise or is it anti-clockwise. You don't care. You just say the total moment M1 is F1 R1. Actually, you know what? Into a force and of a force. Force times distance. Yes, it's not distance times force. Okay, that's the wrong. That's a very bad example. Moment of a force. It's R times F. I'm very sorry for that. It's not F times R, it's R times F. And that is that is different. F1 cross product. Yes, the order of vectors matters in a cross product. It's anti-commutative. That means in cross product, A times B is equal to minus B times A. So that's I mean, look, I can go on forever. I can do a whole session on this. let's not go into that. The point I was making that vector is a the momentum is a vector quantity. And we know that because mass is scalar and v is vector, so it has to be a vector. Now, in an isolated system, momentum is conserved. That's what they say. In an isolated system, system, the total momentum is conserved. Now, when you did GCSE, they told you momentum is conserved. Now it's a slightly, in A level, you have a slightly better definition. In an isolated system, momentum is conserved. So that's important. The isolated system means no external forces. So let's prove that. Let's prove that for 3 objects, for example. Let's say we have 3 objects to prove conservation of momentum formally. 3 objects, and object 1 of mass m1. Let's object 2 of mass m2 and object 3 of mass m3. And let's say object 1 interacts with object 2. So that simply means that there's a force between them. So let's say object 2 attracts object 1 with a force F1 from 2. According to Newton's third law, well, there has to be an equal and opposite force of attraction, which is F21. So the 2 objects attract. Now, imagine M2 and M3 also attract. So let's call it like this. F2 from 3 and F3 from 2. And imagine these M1 and M3 also interact, and they repel for some reason. We don't have to know what's happening. So this is F1 from 3, and this is F3 from 1. In addition to that, we have 3 external forces. Let's call it F1, F2, and F3. They're external forces. F1, let's call it X, F2 X, and 3 external. Okay. Now, writing down Newton's second law. Second law. That m1 times acceleration 1 is a vector is equal to F12 plus F13 plus F1 external. M2A2 is going to be F21 plus F23 plus F2 external. Yeah, does everyone understand what I'm doing so far? Do you understand how I'm using Newton's second law? Mass acceleration equals the total force. Yes. Newton's second law. Mass acceleration equals the sum of forces. So for the first object, mass acceleration is the sum of the forces acting on the first object. The mass times acceleration for the second object is the sum of forces acting on the second object. Yeah, does anyone understand? Yes or no? Or maybe on a scale from 0 to 10? I got seven replies. There's 17 of you. So is that 10 zeros? Is that 10 fives? What should what is this? What am I supposed to think? All right. Okay. So Tom, can I? Is there anything in particular? I'll just go through again. So if you have an object and there are several forces acting on it. So for example, F1, there's a force, another force, F2, and F3. Newton's second law says that mass times acceleration, so this is the mass of the object, is equal to the total force. So mass acceleration is equal to F1 plus F2 plus F3.
Okay, I get that now. Thanks.
Okay. So I'm doing the same just for three different objects. M1A1 is F21 plus F13 plus F1 external, because there are three forces on object 1. There are three forces on object 2, and similarly, there's three forces on object 3. M3A3 is going to be equal to F31 plus F32 plus F3 external. Okay, so acceleration is the change in velocity. Acceleration is the change in velocity divided by change in time. We all know that. So we can write this as m1 delta v1 divided by delta t, because time is the same for all three objects. M2 delta v2 divided by delta t, m3 delta v3 divided by delta t. And now what we're going to do is we're going to add the three equations. Oh, no, sorry, multiply all the equations by delta t. Just one sec. Doesn't look right. Yeah, okay. Yeah, well, we're going to add the three equations. I'm going to hold on with this for now, just not to make it too clunky. Okay, I'm gonna add the three equations. And here I got m1a1 plus m2a2 plus m3a3 equals. Now you will notice that this and this cancels out when we add them. This one cancels out with this one, and F13 cancels out with this one. So we have F1 external plus F2 external plus F3 external. And now we rewrite this as M1 delta P delta V1 divided by delta T. And you notice that delta M1 delta V, that's change in momentum. So we can say this in change in momentum 1 divided by delta T plus change in momentum 2 delta t plus change in momentum 3 delta t, because change in momentum is equal to mass times change in velocity. And we have the sum of F external forces. I'm going to simplify it to the sum of external forces. And now we multiply everything by delta t. So delta P1 plus delta P2 plus delta P3 is equal to the sum of the external forces multiplied by time, by change in time, of course. By time. So this is the total momentum, total change in momentum. Total change in momentum. And now we come to something exciting, or maybe the opposite. Maybe the opposite is exciting. Maybe something very dull. The total change in momentum. So we can, the total change in momentum is equal to 0 if the sum of the external forces is 0, or or each F external is equal to 0. So if this is 0, if the external forces is 0, so if it's a closed system, that means in a closed system, the sum of external forces is 0, or just no external forces. And therefore, total change in momentum is 0. So we've proved conservation of momentum using Newton's second law. Well, impulse is force times time. Yes. This is also known as impulse. Change in momentum, aka impulse. Impulse. So we formally proved that conservation of momentum is a consequence of Newton's laws. Newton's second, we've used Newton's third law, we've used Newton's second law. And Newton's laws are useless without Newton's first law, which talks about international frames of reference. So we've used all three effectively. Okay, moving on. Now we're going to do some reasonably easy questions. A mass m traveling at 5 meters per second collides with an identical mass traveling at 3 meters a second in the same direction. After the collision, the masses stick together. What is the speed of the new mass? So we have a mass m and another mass m traveling in the same direction. So which one is moving faster? Formal proof, or just a proof? Like when I say formal, it just means with clearly stated assumptions and clearly clear consequence. Basically, the consequence is from here we've proved that this definition, this proof can be expanded to 4 bodies or 5 bodies. We're not limited. And a closed system, a system with no external forces. So, for example, Well, if you imagine a snooker table with no friction, outer space, yeah, outer space would be one. When you, not just outer space, it has to be far away from any planets. It's not enough to go into orbit. Okay. Reasonably simple question. So we have this one is, of course, is 5 meters per second, and this is 3 meters per second. So we draw this arrow longer, and they collide. So momentum is conserved. That means momentum before is equal to the momentum after. Let's do a slightly formal approach. We're gonna go the total change in momentum is 0. The total change in momentum is 0. It means the change in momentum of the first body plus change in momentum of the second body is 0. Change, by definition, is final minus initial. So that means P final minus P initial for the first body plus P2 final minus P2 initial equals 0. And we have P2 final minus P plus P1 final plus P2 final has to be equal to P1 initial plus P2 initial. We usually write P1 plus P2 is equal to P1 dash plus P2 dash. Whereas this is before the collision, and this is after. So it's a formula you probably have seen before, which can also be rewritten as M1U1 plus M2U2 equals M1V1 plus M2V2. Yeah, familiar to you? I'm just showing where this formula comes from. So this comes from this statement. It's a consequence of this statement. It's a good thing to practice. Okay. So the two masses collide and they stick together. And now their mass, so this is M, this is M, this is 2M. And it's traveling at V. So I write M1 U1 plus M2 U2 equals M1 V1 plus M2 V2. And here I can just say, okay, M1. So it's M times 5 plus M times 3 equals M, which is 2M, well, M. Technically, they're both moving with the velocity V, so mv plus mv. Okay, and you can divide by m. You can divide all the equation by m, and you get 8 equals 2v, and v is equal to 4 meters per second. Quite an obvious result, because if you have 5 and 3, they stick together, the combined velocity is 4. Okay, easy? Type 1 if you found it easy, please. Okay. Oh, what am I doing? Okay. A gun on rails is moving with a velocity v. The gun shoots a projectile in the direction of travel at angle alpha. As a result, the velocity of the gun decreases by a factor of 3. What is the velocity of the projectile? Mass of the gun is m, mass of the projectile is m small. Now you would think that this is different from the previous question. It actually isn't. Let's see. So we need to draw the situation beforehand. So we need the before scenario and the after. So copy. So before and after. Before, after. We need to understand that the projectile is inside, and here the projectile is outside. It's been shot. Okay. Before, both the gun and the projectile are moving with velocity v. And here, the gun is moving with velocity v divided by 3, because the velocity becomes 3 times less. And the projectile is traveling at an angle with velocity v. Now, the beautiful thing about conservation of momentum that it is all about vectors, and vectors are all about projections. So momentum in any given direction is conserved. That means we can make a projection onto the x-axis. So if momentum is conserved, it is conserved in any given direction. Or it could be conserved in a given direction. Momentum can be conserved in a given direction. Momentum can be conserved in any given direction. Okay, so if you look carefully, you will see that initially the momentum is only horizontal. The gun is only moving horizontally. But after the collision, some part of the gun, though, so the projectile is not moving horizontally, it's moving vertically as well. So momentum is not conserved. Can somebody explain why? Somebody tell me why momentum is not conserved. Vertical momentum momentum is not conserved. Exactly. Thank you, Archie. There is the reaction force from the ground is the external force. There is an external vertical force, which is the reaction from the ground. So when the gun shoots, the reaction force from the ground increases, and that causes the system to change momentum. But horizontally, there are no external forces. So horizontally, momentum is conserved. So there is a vertical force. There is a vertical force. Vertical force. Reaction from the ground. From the ground. The ground. But horizontally, we have no external forces. And therefore, we can write Newton's second law, or sorry, conservation of momentum horizontally. So all we need is so m plus m, that's the total mass before, multiplied by v, capital V, or just reaction force from the ground. So look, when the gun is stationary, there is the mg force, and there is the normal reaction force. But when the gun is shooting, at the moment when it's shooting, for a very short time, mg is the same, but the reaction force is increasing. Why? Well, because the gun is shooting the bullet, it's pushing the bullet that way. The gun is pushing the bullet that way. That means the bullet is pushing the gun into the ground. So this is the force from the bullet. And this is why, first of all, this is the force that causes the gun to slow down, change momentum horizontally, and also that increases R. So R is an external force which causes the system to change momentum. Right, so the total mass before the collision is m plus m times v equals, now this is just m plus m, because there's no bullet inside, so it's m multiplied by v divided by 3 plus the momentum of the bullet, of the projectile. And the momentum of the projectile is mv cos alpha, because alpha is the angle. And what are we looking for? What is the velocity of the projectile? So v, small v. Okay, so mv plus mv equals mv over 3 plus mv cos alpha. So mv, that's 2 mv divided by 3 plus 3 mv divided by 3 equals mv cos alpha. So 2m plus 3m divided by 3m cos alpha multiplied by v, that's equal to v. That's the answer. Okay. There's a second part to this question. Imagine the gun was immobilized. That means, well, stuck into the ground. How would the conservation of momentum apply in this case? So here we have what? The gun is traveling at velocity v, it's shooting a bullet, and it's slowing down because of that. And imagine it was immobilized. So imagine it was stuck in the ground. How does the conservation of momentum apply? Because you have zero momentum at the start, but the bullet has momentum and the gun doesn't. So therefore, momentum is not conserved. Of course, it's not conserved because there's an external force, which is the ground. The friction from the ground is the external force. But it's quite uncertain. Like, what's going on? Like, why? I mean, if we take the gun and the earth as a system. So let's say this is planet Earth. And planet Earth is rotating. And if you have a gun here, and you shoot the gun, as a result of your shot, because there's a recoil on the gun, the Earth slows down ever so slightly as the gun shoots. The gun shoots. The planet slows down. Down. But there's a problem. Do you see the problem? The gun and the planet have to be is an isolated system. So the gun cannot slow down. Yeah, it could. It could speed up if you shoot the other way. It could make the planet speed up. But you cannot cause a change in the rotation of the Earth using internal forces. And because that's an internal force, if the gun and the bullet is a closed system, then it's an internal force. And eventually the planet has to speed up again. So when does it speed up? No, it speeds up when the bullet hits the ground. Speeds back up. Slows down. It speeds back up when bullet hits the ground. So it just causes the planet to go slightly slower, but when it hits the ground, the planet starts moving slightly faster. And exactly this happens when it's very realistic. It's just The change in the velocity of the Earth would be very small. So small that you won't be able to measure it. But this happens every time you jump. When you jump into the air, the Earth moves slightly down. And as you come back up, the gravity pulls the Earth back into place. Because the total momentum cannot change. The total momentum is conserved at. We were not able to find anything that violates the conservation of momentum. We have found violations of conservation of energy, but we have never found violations of conservation of momentum. I think that's a correct statement. Right? Subatomic particles, they violate conservation of energy for a short period of time. Okay. Okay, now we move into 2 dimensions. So as I said, momentum is conserved in all directions. So a male and female skater of equal mass are moving as shown in figure 2. The female skater is moving at speed UA at an angle of 45 degrees, and the male skater is moving with the same speed above the horizontal. When they collide, they cling to each other, and both of them move horizontally velocity v. What is v in terms of UA? So it's quite straightforward. So we have both of them 45 degrees, so that makes life easier. So we have the female skater traveling at velocity UA. And we can immediately split that into horizontal and vertical. So horizontal and vertical. This is UA cos 45. This is UA sine 45. The male skater, so that's MA, MB, and they also UB, UB cos 45, UB sine 45. And when they collide, they move together with velocity v. So this is MA, this is MB. Okay, so that's fine. We have conservation of momentum vertical in the vertical direction. In the vertical direction. We have MA. We can say this is the positive direction. MA, and this is the horizontal direction. MA is MA, so minus MA UA sine 45 because it's moving down, plus MB multiplied by UB sine 45 equals, and now they're not moving vertically anymore. After the collision, it's 0. Horizontally, we have momentum before is equal to momentum after. So we have MA UA cos 45 plus MB UB cos 45 equals MA plus MB. They move together with velocity V. UA. Okay. So from here, from the first statement, we can see that M A U A sine 45 equals MB U B sine 45. So sine 45 cancels, and we have UB is equal to MA UA divided by MB. And we can substitute that into here. So MA UA cos 45 plus MB multiplied by UB, which is MA UA MB. Ooh, interesting. MB cancels. Cos 45 equals MA plus MB multiplied by V. And here we can have V is equal to MA 2 MA UA cos 45 divided by MA plus MB, which is cos 45 is square root of 2 over 2. So it's square root of 2 MA UA divided by MA plus MB. That's the solution. What if the bullet exited the Earth's atmosphere? Well, you would, well, it depends. If it exited the Earth's atmosphere and came back in, nothing different. Also, but if it left the gravitational field of Earth, if it went at the second cosmic velocity, because second cosmic velocity is the speed needed to leave the Earth forever, then you would consider them still as two separate bodies. Yes, the Earth would not slow down. Yeah, effectively, if you send a rocket into deep space, yes, the overall the velocity, the speed of Earth changes. True. No, a nuclear explosion would not even a nuclear explosion, even the biggest nuclear explosion that we have seen, would not make it measurable. We can calculate theoretically, but not. Do we? Of equal mass. Oh, of course. Sorry. Then life's easier. So that's just 2. Square root of 2 over 2 UA. That's it. Okay. Because the mass is equal. Now the same skaters. Same male and female skaters, equal mass are moving again. But this time the female skater is moving with speed UA at theta below the horizontal and half that speed. So we already know that UB is 1/2 UA. So in the vertical direction, we have minus MA UA sine theta plus MB UB sine theta equals 0, sine phi Sine phi equals 0. And from here, we can work out that, we already know that UB is 1/2 UA. MB is 1/2 UA, so that's going to be 1/2. So, and UA can cancel. So MA sine theta is equal to MB sine phi divided by 2. Oh, we know that the masses are equal. Okay. Masses are equal, so we can cancel them as well. So 2 sine theta is equal to sine phi. Now horizontally, actually I would modify this problem. I didn't see that they were the same mass. I would modify this problem not to have the same mass. Okay, let's make a different mass. That makes it more interesting. So masses don't cancel out. So 2 MA equals MB sine phi. Perfect. Now horizontally we have MA UA sine cos theta, cos theta plus MB UB cos phi. All right. Okay, say hi to your tutor. Right, and then MA plus MB times V. Okay, now we have we can substitute that in. So we have MB is equal to 2 MA sine theta divided by sine phi. So MAUA cos theta plus MB, which is 2 MA sine theta divided by sine phi multiplied by UA divided by 2 divided by cos phi equals MA plus MB times V. What is the value of sine phi? Well, from the question that they're asking, sine phi is going to be, of course, 2, so 2/3. What is V in terms of UA? And V is equal to MA UA open bracket cos theta plus 2 cancels sine theta divided by tan psi phi, and is in divide over MA plus MB. And of course, if they're the same, V is equal to UA divided by 2 multiplied by, if MA equals MB, UA over 2 cos theta. Cos theta. So we know sine theta. Cos, we need cos phi. Sine. So here we use trigonometry. So sine theta is 1/3. Sine phi is 2/3. Cos theta is 9 2 square root of 2 over 3. Yeah. And cos psi is 4 5 square root of 5 over 3. Okay, and then you get 2 square root of 2 over 3 plus sine is 1/3 divided by tan phi. Tan phi is going to be 2 divided by square root of 5. Okay, so V is going to be UA over 2 multiplied by 2 square root of 2 over 3 plus square root of 5 over 6, 4 UA divided by 12, 4 square root of 2 plus square root of 5. So something like that. Okay, so I hope that makes sense. I mean, the maths is not particularly interesting here, but what you need to understand here that conservation of momentum happens in the vertical direction and in the horizontal direction separately, and that's really important. Okay. Problem 6 and problem 7. Now we need to merge conservation of momentum and conservation of energy. This is called a ballistic pendulum. A ballistic pendulum is a method of measuring the speed of very fast objects, such as bullets or pellets from a pellet gun. And as a student, we did an experiment. We had a pellet gun and we shot it at a pendulum, and we saw how at the movement of the pendulum after the bullet is shot. So what happens is you have a pendulum, and a pellet from a pellet gun is traveling at velocity, let's call it u. The mass of the pellet is m, and it hits the ball of mass m, and as a result, the pendulum starts swinging. And we are given the amplitude of the swing. The amplitude of the swing is 8 centimeters. The length of the rope is 1.5 meters. And the mass is 0.4 kilograms. Okay, so happy with that? I wonder if I can find a video of a ballistic pendulum. Ballistic pendulum. Pretty much.
This is the ballistic pendulum. It will be the subject of one of the labs that you will do fall and help the pendulum to swing right. Cock the gun and then get this pendulum stationary and then pull the trigger and hope for the best. 0, 1, well, 3, 2, 1. Okay, so what you've seen is.
So yeah, the ball hits the pendulum and it swings. Well, now this one stops. It is stopped by friction, but sometimes they're not. They're different types of ballistic pendulums. Here's so here's some kind of gun. So basically, yeah, that's the ballistic pendulum. All right, so by measuring the amplitude, we can find, using conservation of energy, is how much the pendulum goes above the starting point. We can find this height. And the potential energy, gravitational potential energy, of course, is mgh, which we already know, which should be equal to the kinetic energy at when it hits. Okay, so where do we start? Well, we start from conservation of momentum. Conservation of momentum. So initially we have the momentum is mu. That's easy. Mu equals. After the collision, we have the bullet and the pendulum are moving. So right after the collision is a bam, and they start moving. So it collides and move. So we have m plus m multiplied by v, which is the final velocity after the collision. All right, so we can work out the speed. The speed is mu divided by m plus m. Okay, so we can calculate. So a mass is 2 grams multiplied by velocity, which we don't know, divided by, so it's 0.4 kilograms, so 400 grams, so 402 grams. Okay, so it's u divided by 201. Good. That's the velocity of the pendulum with the bullet after the collision. Now we do conservation of energy. Conservation of energy. Just after the hit, the pendulum has kinetic energy. So kinetic energy is equal to gravitational potential energy. So kinetic energy is 1/2 m plus m multiplied by v squared equals to m plus m, because the total combined mass is m plus m, gh. So m can cancel, and we're left with h is equal to v squared divided by 2g. And we already know that v is u over 201. So there's going to be u squared divided by 2, or 2g, 2 times g times 201 squared. That's the height. That's the height at which the maximum height of the pendulum. Next part is using the height to work out the amplitude. Well, I mean, to link the height and the amplitude. So if the pendulum is like this, and now the pendulum is like this, so this is, oh yes, sorry, Yeah, I've changed I've changed the numbers. You know what? Let's just b squared, which is m squared u squared divided by 2 m plus m squared g. Let's keep it that way. Okay. Let's keep it in terms of m and then substitute everything in the last moment because I did 2 versions of this problem and okay. Now let's say this is the length of the radius of this swing, the radius of the rope, which is r. R is the length of the rope. Why r? Because it's the radius of the circle. I like it more like that. So if we draw a line like this, and this angle, let's say this angle is theta, is the maximum angle, maximum angular amplitude. So the height, this is the height. The height is going to be equal to r, which is this one, minus r cos theta. Okay, so the whole thing is r, and this is r cos theta because it's a right angle triangle. So the height, this little bit, is r minus r cos theta. Okay, so what we have is r minus r cos theta equals m squared u squared divided by 2 m plus m squared g. So we can divide by r. So cos theta is going to be 1 minus m squared u squared divided by 2r g m plus m squared. Okay, so I made cosine the subject of the formula. I made cosine the subject, and because we know the amplitude is the horizontal displacement. Amplitude let's call it A. A is equal to r sine theta, approximately, because it's a small angle. It's going to be r sine theta. So this is the horizontal displacement, the amplitude. Right. So, but we have cos theta. It's a bit annoying. But so A squared equals r squared sine squared theta divided by r. So a squared over r squared equals sine squared theta. 1 minus cos squared theta is equal to a squared over r squared. And then cos squared theta is equal to 1 minus a squared over r squared. If you want to. So cos theta is that. And now you have square root of 1 minus a squared over r squared equals 1 minus m squared u squared over 2rg m plus m squared. And of course you can work out u from here. I don't want to do the whole equation. I mean, I would work out in steps. So I start with the angle. I start with sine start with the angle. So from here, sine theta. Okay, so my point is, you can work out u from this equation, and it's not particularly hard. Like honestly, it's going to be m squared u squared over 2rg m plus m squared equals 1 minus square root 1 minus a squared over r squared. Then you multiply everything by this and divide by m squared. So u is equal to u squared is equal to 2rg m plus m squared divided by m squared, open bracket, 1 minus square root 1 minus a squared over r squared. And then you remove the square and just put the square root in, and that's your answer. That's the speed of the bullet. I mean, it's not ideal, but alternatively, you can do it with numbers. But this formula, I mean, that's the beautiful thing. You give this formula to a monkey and they can do it, right? I mean, people don't need to know physics. So somebody working at a testing facility, at a bullet testing facility, they don't need a physics degree. All they need is a formula, and they substitute the mass of the pendulum, the mass of the bullet, gravitational field, the length of the rope, and you got the speed. You can work out the speed of the bullet. That's yeah. So if ever you're designing, if you're designing a ballistic pendulum, that's the formula for it, and that's why we spend so much time teaching you how to work with formulas. That's because that's a huge part of physics, and there's a lot of fun in it. Honestly, I find it very fun getting an expression and it working. Finally, it working. But we can go the alternative way. We can say, all right, well, we know that the amplitude is what, 8 centimeters. 8 centimeters. Alternative way. The amplitude is 8 centimeters. And that means we can find the sine of the angle. Sine theta is amplitude divided by the radius, which is 8 divided by 150 centimeters, which is something. 8 150, which is 0.05333. So that means the angle is 3.06 degrees. That's the angle at which the pendulum swings. It's the angle of the swing of the pendulum. And we can work out the height. H is equal to R 1 minus cos theta, which is 150 times 1 minus cos 306. So 150 multiplied by open bracket 1 minus cos answer 0.213 centimeters. which is of course 0.00213 meters. So the velocity from here, you can work out velocity u squared is 2m plus m squared g divided by m squared multiplied by h. So divided by 100 multiplied by 2, open bracket, mass, which is 0.4. Well, you don't have to do it in, you can do 405 squared, close bracket, multiplied by 10, divided by 5 squared, 208a. So u squared it's way too small. Okay, well, I hope I didn't make a mistake. Well, you can check my working out later on. And so u is going to be u squared is going to be 280 meters squared per second squared, which is so u is square root of that, 16.7 meters per second. It doesn't strike me as reasonable. It's a very small speed for a bullet. 5 grams at 16 meters per second. That's what was in my initial calculation. So I might have made a mistake here. Let's see if we can do this formula. 2 multiplied by is 1.5 multiplied by bracket 405 squared divided by 5 squared multiplied by open bracket 1 minus square root 1 minus amplitude is 8 over 150 squared. Good 5. That's weird. Sorry, I've made a mistake somewhere. I'm not sure where exactly. Doesn't strike me as a reasonable answer, but I think you got the gist of how to do it. So yeah, somewhere I got lost in the math, so apologies for that. Let's go backwards. So let's say the bullet was 200 meters a second. 405. Yeah, so imagine the bullet was 200 meters a second. U is 200 meters a second. That's a more reasonable. That means the velocity would be. No, sorry. Let's not confuse each other. Right. And also I don't have the time to finish it. So yes, let's keep it like that. If you find an error, if you find my error, let me know. I'll finish here. hope this was useful. If you still have doubts about momentum, please watch my other webinars. Yeah, that's it. So I'll see you all next week then. See you. Welcome.